Thank you very much for that introduction, David. I appreciate that. And to you too, Tebi Madupi. Now, Tebi and I have known each other for many years, as he said, since he was a student. My first visit here to Mahakeng and to Northwest University was at the time of this conference, and you can see the conference photo up there. At that time, Tebi and I were both younger, of course, as we all were, and there you can see us on my first visit. Tebi Madupi worked for many years to make it a reality that I could come here and have this extraordinary professorship. I'm delighted with that. I'm happy that my retirement has brought me back to South Africa, where most of my adult life is, and it's where my heart is. This is where I live. I do visit the UK too, but South Africa is my home. Today, I want to take you on a trip. One of the deepest questions we humans can ask is, are we alone? Are we the only intelligent creatures in the universe that look out and wonder about it? Is Earth the only planet that has life on it? And in a future public talk, I will do many of these. I will tell you the story of the more than 4,000 planets we've discovered around other stars. But to understand those, we need to understand our own planet. We need to understand our own solar system. Those are the best examples we've got. And so today I'm going to tell you about the very fine balance of the Earth's position near the sun, sandwiched between the 15 million degree nuclear inferno at the core of the sun and the absolutely frigid, icy outer solar system. If you'd like to think about what the solar system is the sun, and that's pretty much it. If you'd like to add a little bit to that, what else is there in the solar system besides the sun? Well, there's Jupiter, the giant planet, and almost nothing else. Now, you and I are very concerned with the Earth, but the Earth is a little rock. And if you add up all the other planets in the solar system, they don't add up to as much stuff as Jupiter. But it's that tiny little third rock from the sun that we're concerned about. And I'm going to tell you about today and put it in perspective to the rest of the solar system as we begin to try to learn to look for life elsewhere in the universe. The sun is powered by nuclear fusion. We discovered that only in the 1920s. A British astronomer named Edgerton suggested the stars might be powered by the fusion of the lightest element, hydrogen, to the next heaviest element, helium. It wasn't known in 1920 what the stars were made out of. That was discovered by the greatest PhD thesis that's ever been written in astronomy, by a young English woman named Cecilia Payne. She would have liked to have gone to Cambridge or Oxford. She was English, but Cambridge and Oxford in the 1920s did not admit women students. So she went to the United States, where she became a student at the Harvard College Observatory, but Harvard College Observatory did not award PhDs to women. And so her PhD was awarded by Radcliffe College, and it is the greatest PhD ever written. She showed that the sun is 90% made out of hydrogen, 8% made out of helium, and it made feasible our understanding that the stars are powered by hydrogen fusion. This is a terrible example you see here on the screen. Once we discovered how hydrogen fusion works in the late 1930s, by the early 1950s, we were making it happen with these horrendous, terrible hydrogen weapons. They still exist in their thousands in the nuclear arsenals of the world, and it should be a goal of humankind to do away with these. That is a bomb test over an island in the South Pacific that back in the 1950s, no one had ever heard of. It's called Bikini. And of course, the word bikini has come into our language as a rather small swimming costume for women, but it is the name of an island which was destroyed by one of these weapons, exploding with the power of about 1 million tons of high explosive. That's nothing compared to what the sun is doing. The sun is fusing 600 billion tons of hydrogen to helium every second. What are we doing with that? We are trying to build nuclear power plants with controlled hydrogen fusion as the energy source for all of humans. The big power plant is being built in the south of France, a place called Cadarache. Its name is ITER, which is now just considered to be a nice Latin word meaning the way, but originally ITER stood for International Thermonuclear Experimental Reactor. It's now a reality being built, and we hope that over the 35 years of the construction of this power plant, it will show that we humans can generate energy from hydrogen fusion, and with that we can stop burning coal, we can stop burning oil, we can stop burning natural gas and pumping carbon dioxide into the atmosphere, something we're going to talk some more about. How will you power your car? You still want to drive, and the answer is easy. With unlimited energy, we will simply separate the hydrogen from oxygen in water, put hydrogen into the fuel tank of your car, and when you burn it, water will come out of your exhaust pipe, and we will not be doing any damage to the atmosphere in doing that. In order to understand the other planets, we need to have some perspective on our own planet. And so here's a picture taken from the space shuttle. You'll see one of the tails on the space shuttle here and its solar panels looking down onto a hurricane, also known as a cyclone or a typhoon, depends on where you are in the world. What you're looking at there is you're looking down into the eye wall of this hurricane, where the clouds stand 20 kilometers high, and the wind speed along the eye wall there reaches speeds of about 250 kilometers per hour. These are the most destructive storms on planet Earth. Imagine when one of these hits. It happens in the United States. You must see it in the news. New Orleans, Miami, Florida. The wind comes in from one direction. Over here at 250 kilometers per hour, it destroys just about everything. And then the eye passes over, the sun comes out, it becomes calm for half an hour, and then the other side of the storm hits and the wind comes back from the opposite direction, still at 250 kilometers per hour, just destroying everything. I'm going to show you a hurricane in a little while on another planet, which is bigger than the planet Earth. This is small stuff compared to what can happen elsewhere in the universe. You might be saying to yourself right now, I just showed you that we've got these big giant hydrogen bombs. They produce radioactivity, that's bad, but there is so much destruction from one of these storms. Why don't we drop a hydrogen bomb into the middle of this storm and evaporate it? And the answer to that is, even my first year undergraduate students can do the calculation, physics students. The power in this storm is 100,000 times more than the power in a hydrogen bomb. And if you drop a big bomb in this storm, the storm will just eat it and not even hiccup. We humans do not have the power to control the weather. That's probably a good thing. We would argue so much over the control of the weather if we could. We astronomers don't want any clouds, we want to see the sky. Professor Medici, who works in plant science, would like to see the rain so the plants will grow. Maybe it's best we don't have control over that. This is a picture in the Grand Canyon, one of the great canyons of the Earth. As one of my adventures, I had a 15-day trip with my wife just a few years ago through the heart of the Grand Canyon in little tiny wooden boats, just 6 meters long. Some of the waves on the rapids in the Grand Canyon are 10 meters high. You hit a 10-meter wave in a 6-meter boat, I can assure you it's exciting. But we also explored, and here we are up at a ruin called the Nankoweap ruin, where the Anasazi people of North America 1,200 years ago would store grain. And we're looking down this great canyon of the Earth, 400 kilometers long, 1.5 kilometers deep, and it is totally dwarfed by a canyon I'm going to show you on another planet in just a little while. The great mountains of the Earth. I did an expedition in Sikkim, which is now part of India, about 10 years ago. It was led by a man named Jamling Tenzing. Jamling's father was Tenzing Norgay, one of the first 2 men to stand on Mount Everest. And Jamling runs a touring company. One of my friends had climbed Mount Everest with him, and Jamling led us on a 12-day walk to the base of Kachinchunga. And so back here in the background behind me, you're seeing Kachinchunga. In that picture, I'm at an elevation of 5,100 meters. The temperature's -10. It's a challenging walk. But there's the 3rd highest mountain on planet Earth, Kachinchunga. If you shrank the Earth down to the size of a billiard ball, the Earth would be smoother than that billiard ball. The mountains on Earth are tiny compared to mountains elsewhere in the solar system, elsewhere in the universe. I'll show you that in a little while too. In Arizona, there's a meteor crater. It's called the Barringer crater, where the Earth was hit about 25,000 years ago by a small rock from space. That rock was 10 meters in diameter, maybe. But with all the energy it's carrying, crashing into the Earth at a speed of about 30 kilometers per second, the energy is released on collision and it exploded, and it blasted out this crater, which is over 1 kilometer across. If you look right here where my cursor is, you'll see some tiny little people standing there having a look at it. The Earth still gets hit by rocks like this. It has its entire life. One of the greatest craters on planet Earth is this one. It's 2 billion years old. It's called the Frida Fort crater, Frida Fort dome. And at this university, one of our main campuses, where the dean has come from yesterday, in Potchefstroom, is just a few tens of kilometers. from this crater. There you can see the Vol River running through the edge of the crater rim. And in the middle of the crater, there's a dome. It's known as the Frida Fort dome. And there's a reason for that dome. Right in the middle of a crater, you frequently get a mountain. There's a schematic map of South Africa showing you where the dome is. Of course, Potchefstroom is there, and we're a little bit further up here in Mahikeng right now. I take you back to the 1930s with this picture. This picture is by a man called Doc Edgerton, who was experimenting with high-speed photography. This red here, this was done in America, is what Americans would call a cookie tin, what we would call here a biscuit tin, for keeping biscuits in. And he has just dropped a little milk droplet down onto the surface with very high-speed photography. The milk droplet has gone splat, and you can see the rim of it here. That's exactly what happens when a rock from space smashes into the Earth. It explodes, it melts the rock, and it sends out a crater rim like this, as you just saw for the Frida Fort formation. And then right where the rock hit, or the milk droplet hit dead center, it bounces back. And that's not the next milk droplet coming in, that's the rebound from the center. And so in the case of a meteor crater, the rock smashes into the surface. Here it happens to be the surface of the moon. This is Crater King, 75 kilometers in diameter. It melts the rock, it punches 10 or 20 kilometers down into the surface of the planet or the moon. And then the molten rock jumps back up and it freezes very quickly. Rock freezes at a high temperature, and you end up with a mountain in the middle of the crater. That's quite common. So notice from the scale of a tiny little milk drop to a gigantic crater, the physics and the understanding of this is all the same. There's a picture of our moon, beautiful picture taken from planet Earth. There's some people in front of it. And if I ask you, what's the color of the moon? You'll say to me, oh, the moon is golden, the moon is silver. We hear the poets telling us that. That's not the color of the moon. The moon is not golden and the moon is not silver. There's an astronaut, 1972, standing on the surface of the moon. Look at the color of the surface of the moon. The moon is black. It's covered in basaltic lava. It has the color of coal and coal dust. Why does it look so bright in the sky? Because you're seeing it against the absolute blackness of empty space. And I'd like you to look in this picture of this astronaut standing here in this big spacesuit. He, and it was all he back then, ladies, I'm sorry, but that's changing. People are going back to the moon soon, both from private corporations and countries. And the next astronauts to go to the moon and live on the moon will be both women and men, not just men. That astronaut is wearing a backpack that weighs 75 kilograms. And in just a moment, I'm going to show you how easy that astronaut can move. If you'll look down at the astronaut's feet, you'll see that he's wearing platform shoes. His shoes have got a thickness of several centimeters. And of course, in 1972, platform shoes were all the fashion. And some of you will know that platform shoes are in fashion now too. If you go to a nightclub, you young people listening in, you'll see a lot of the women wearing high heel shoes with very thick platforms for fashion reasons. Is this astronaut fashion conscious? Was NASA concerned about fashion, sending an astronaut to the moon with these beautiful platform shoes? And the answer is no. Here in Mahikeng, in the summertime, the sun beats down on the ground. And even if you've got tough feet, if you've grown up barefoot your whole life, as many people who grow up here do, you need mighty tough feet to walk out onto a tarmac road in the middle of summertime because the ground temperature can reach 65 degrees Celsius. Why doesn't it get hotter? The answer is because the Earth has an atmosphere. We have air. The air heats and the hot air rises and carries away the heat. The moon's the same distance from the sun, but it has no atmosphere. It's too small to keep an atmosphere. That astronaut is standing on ground that has a temperature of 100 degrees Celsius, and he's wearing platform shoes to keep from frying his feet. Now, the astronauts, when they were on the moon, moved around. The technology back then was not like it is now. It was just very primitive video cameras. But let's watch these astronauts on the moon taken with an old-fashioned video camera as they move across the surface.
I was rolling on the moon one day in a merry month of December. May, when much to my surprise, a pair of early eyes. Oh, this is a neat way to travel. Isn't it great?
Look at them bouncing.
Skip along, not me, boy.
All right, several things are happening there. First, These guys are on the moon. They are really hyped up. They're excited. If you were on the moon walking around, you'd be excited too. But even with those 75-kilogram packs, you saw how that man was bouncing. The moon has gravity only 1/6 the Earth's gravity because it's smaller. And when we next send astronauts back, we'll put a plexiglass dome over a crater. And the rock on the moon has plenty of oxygen. We'll pump the dome full of oxygen, and then they'll be able to move around dressed as you're dressed right now, just in normal clothes. And think of what they'll be able to do. It's only 1/6 the gravity here on the Earth. Somebody who can jump here on the Earth, basketball player, high jumper, ballet dancer, gymnast, can get their center of mass about 1 meter off the ground. On the moon, 6 meters. For those of us sitting together in a room right here, if this was on the moon, I would have no trouble whatsoever standing up and jumping up right to the ceiling. No trouble. We all love to watch as we're driving across the countryside here in South Africa, the antics of our vervet monkeys and our baboons as they scramble up trees and they climb rocks. Humans on the moon will have the power to weight ratio of baboons and they'll be able to climb. Sport will be fantastic. Play cricket, you're going to be able to hit the ball a kilometer. You're going to need binoculars to play a game like that on the moon. It's coming. People will go back to the moon. They will be working, but they will also entertain themselves. And so that's what it's like if you're going to live on a small body with low gravity. Now, this picture is spectacular. This is not photoshopped. Look at it and see what you can see. Of course, there are clouds, and there's a little crescent right here, and you might think that's the moon, but that's not the moon. The moon's in this picture. Look at this very thin, faint crescent I'm running my cursor along right here. That's the Earth's moon, and it's about to pass in front of the much more distant planet Venus. Venus also has phases, and through a small telescope, you can see it as a crescent, as in this beautiful picture here. Venus is the second planet from the sun. It's only slightly smaller than the Earth, and it's only slightly closer to the sun, and yet it is completely unlivable. You're looking at the atmosphere of Venus there. It has a thick atmosphere, 30 times the mass of the Earth's atmosphere, 96% made of carbon dioxide. If you go to Venus, when I was a child, we thought that perhaps, I was a child in the 1950s, we thought perhaps there might be life on Venus. Then we discovered the atmosphere is made of carbon dioxide. Now, we are sitting here breathing right now, 78% molecular nitrogen, 21% molecular oxygen, 1% argon, a little bit of water vapor, a little bit of other elements, a little bit of carbon dioxide. 96% carbon dioxide, you're going to suffocate. That atmosphere is so thick that the pressure at the surface of Venus is 90 times the atmosphere here on the Earth. That's the pressure in the ocean if you're to dive down almost a kilometer. For you and for me, if we go to the surface of Venus and we don't have protection, we will be crushed. We will be suffocated. But the important thing is carbon dioxide is a greenhouse gas. It lets visible light through to the ground heats, and then it radiates long wavelength infrared light. We can't see infrared light, we feel it as heat. The carbon dioxide traps that heat. That's happening here on the Earth now. We're pumping carbon dioxide into the atmosphere. That's trapping more heat. We're changing the climate of the planet. We'll come back to that. On Venus, it's had a runaway greenhouse. Temperature on the surface of Venus, 470 degrees Celsius. You go to Venus, you're going to be fried too. And then in the 1960s, a good friend of mine from Southern California, his name's Andy Young, working at the Jet Propulsion Laboratory, discovered that these clouds you can see in this picture of Venus are made of concentrated sulfuric acid. You go to Venus, you're going to be crushed, fried, suffocated, and dissolved. This is not a place to live, and yet it's only slightly closer to the sun. If the Earth were a little bit closer to the sun, we would be like this too. We sent a mission to Venus, and we orbited Venus for years with something called the Magellan mission. It had radar on it, and it bounced radar beams off the surface, and we could use that to map out the surface of Venus. We've artificially colored it in this picture with orange light because very little light from the sun gets to the surface. But there you can see the topography of Venus. It's much more volcanic than the Earth. It's covered in lava flows, live volcanoes. And if you look carefully, this picture is about 40 kilometers on a side. And running across the picture from top right, if you follow my cursor, there's a river channel here. You possibly can see it looking at this picture. There's a river on Venus. And yet think about what I just told you. The temperature is 470 degrees Celsius. There's no water on Venus. What carved that river? And the answer is lava. Here on the Earth, there's an erupting volcano, and there's a river of lava carving a river channel through basaltic rock here on the Earth. The lava on Venus is much less dense than here on the Earth. It's much more viscous, and we think that the rivers on Venus flow for thousands of years and carve out river channels. Well, that leads me to a very important topic, volcanoes. Just a few weeks ago, the great volcano in Sicily in Chile erupted again. It's named Mount Etna. I have walked almost to the top of Mount Etna. The ground temperature below your feet there is about 50 degrees Celsius. If you dig down just a few centimeters, it'll absolutely fry you. When the volcano is not erupting, you can walk there, but right now you can't walk there. This is live from just last month. The lava fountain is shooting 1,500 meters into the air. Those great blobs you see there are huge molten blobs of rock smashing into the ground. Obviously, nobody is up climbing on Mount Etna right now. But volcanoes are very important in the history of the solar system. They're very important to the formation of atmospheres on planets. Here in real time is an erupting volcano where you can see an ash cloud coming out of that volcano. This is where the atmosphere of planet Earth came from. When the solar system formed 4.65 billion years ago, the sun was spinning and it spun off a disk of gas and rock. And out of that disk, as it cooled, the planets formed. Rocks smashed into each other, bigger and bigger planets formed, but at first the rocks were hot, they were molten. And then the Earth cooled, and as it cooled, the volcanoes erupted like this one you're watching it. And they belched out ash, of course, you can see that, but mostly they're belching out gases, and the main gas, carbon dioxide, with a little bit of nitrogen. And so we think when the Earth formed, it had an atmosphere just like Venus's atmosphere now. 96% carbon dioxide, 3% nitrogen. But what happened with the Earth is it was just far enough from the sun that the water condensed into oceans. And in the oceans, the carbon dioxide dissolved. It interacted chemically with calcium, and for those chemists in the audience, and it formed calcium carbonate, limestone. And around the world, we have great layers of limestone in many places. Here in South Africa, outside Oudtshoorn, because somebody in the audience is from Oudtshoorn, Dean. And of course, the Congo caves are in limestone, which dissolves nicely in water. That tied up all that carbon dioxide in the Earth's atmosphere, left behind the nitrogen atmosphere we breathe. And then here on this planet, somehow, we don't know how yet, life formed. And of course, plants breathe in carbon dioxide, they breathe out oxygen, and that then changed our atmosphere to be this atmosphere of nitrogen and oxygen, which allows us to breathe and gives us this wonderful environment that allows life as we know it. These volcanoes are still dangerous. Here's another real-time eruption. And that gas cloud that you see rushing down the hill is concentrated carbon dioxide. It's full of dust, and the temperature inside that cloud is about 300 degrees Celsius. It's coming down the hill at 150 kilometers per hour. And when this happens on Earth, if you're downstream, you're not going to get away from that thing. These are deadly. This is a gigantic rock here, much bigger than your house. And watch what happens as that gas cloud smashes across that rock. You don't have a chance. This is what happened in 79 AD in Pompeii, below Mount Vesuvius, just outside the modern giant Italian town of Naples. And there are what's left of the bodies of some of the people who were caught by that cloud. Naples is below Mount Vesuvius. It will erupt again. It one day will cover Naples with a gas cloud like that. Hopefully with enough warning that the people who live there can run away, but they will lose everything. We can't stop this. It will happen. The positive thing, this is where atmospheres come from. It's why we've got this wonderful atmosphere here on the Earth. And so there is our beautiful blue planet. Not so close to the sun that it's fried by those high temperatures. We're not like Venus. But I want you to look at this. Of course, I picked a picture with everybody's favorite continent in it. This is our continent, Africa. And of course, down here in South Africa, there's a cold front, by the way, going through the Cape and the South Coast. Up here where we are, there's the high veld. Here we are up near the Botswana border in Mahakeng. But I want you to look at that picture. Can you see the atmosphere? No. The Earth is 6,400 kilometers in radius. It's 12,800 kilometers in diameter, but the biosphere, the atmosphere, is only a few kilometers thick. so thin you can't possibly see it here. And we humans, almost 8 billion of us, are changing that atmosphere. And for us and for the other things that live on this planet, not for the better. Here is a graph showing the carbon dioxide in the Earth's atmosphere in the middle of the Pacific Ocean on the great Hawaiian island of Hawaii itself. One of its volcanoes, which is now dormant, is called Mauna Loa. It's got an observatory out in the clean air of the Pacific, which is measuring the amount of carbon dioxide in the Earth's atmosphere in parts per million from before the 1960s up to the present day. You'll see a wobble in this picture. That's the annual change in carbon dioxide, because plants breathe in carbon dioxide, they breathe out oxygen, and most of the plants in the world live in the northern hemisphere because most of the continents are in the northern hemisphere. So the great forests of Russia, Alaska, Canada are causing this to change on a yearly scale, but look at the way the carbon dioxide level's going up with time. That's us. That's you, that's me. We get in our cars, we drive around in our cars, we burn coal to produce the electricity for our technology. We need those things. We need those things for our lifestyle in order to give people a better life, to raise the economy so that everyone can live comfortable lives and we're not leaving people in poverty. We can't stop producing electricity, but to stop changing the climate, to stop global warming and climate change, we need this curve not just to stop climbing, not just to level out, we need it to come back down again. And if you look right there, we're not succeeding right now. For those of you who intend to be politicians, who intend to be technologists, who are going to work on this problem, you have a big challenge. And the challenge is economic too. We need the energy. So there from our beautiful Earth, let me take you farther out in the solar system to the next planet out, Mars. Mars is 50% further from the sun than the Earth is. It's about half the size of the Earth. It has an atmosphere, very, very thin, but it does have an atmosphere, and that atmosphere is made out of carbon dioxide. Carbon dioxide is what comes out of the volcanoes, and boy, does Mars have volcanoes. But first, what I want you to notice in this picture you're looking at now is the Great Valley on Mars. We call it the Valles Marineris, in Latin, the Martian Valley. Here it is stretched across the planet. If we could bring that valley here to the Earth, it would stretch from where I'm sitting right now, in Mahakeng, those here in the live audience too, it would stretch from here to Nairobi. And along the way, it would pass through Tanzania. And we could have it pass by Mount Kilimanjaro, the biggest mountain in Africa. Mount Kilimanjaro is 6 kilometers high. This canyon's 6 kilometers deep. If you put Mount Kilimanjaro in the bottom of this canyon, it would only just reach the rim. If you look at where my cursor is right now, there's a tiny little side canyon right here off the Valles Marineris. If you follow my cursor, that canyon right there is the size of the Grand Canyon on the Earth that I showed you a little while ago. You thought the Grand Canyon was big? I did too when I was in it. But there it is on Mars. It's just that tiny little thing. And here's the Great Valley on Mars. Up here in what we call the Tharsis Bulge are the great volcanoes on Mars. And let me show you one of those. This is, we called it Olympus Mons, after Mount Olympus, where the Greeks traditionally 2,000 years ago believed that their gods lived on top of their mountain, Mount Olympus in Greece. Mount Olympus is only a couple kilometers high. This great volcano on Mars stands 23 kilometers above the surrounding plain. Mount Everest here on the Earth, 8.8 kilometers above sea level. Olympus Mons, 23 kilometers high. And from one side to the other, 600 kilometers across. And so if we imagine Mabate right here in the crater at the top of Olympus Mons, if we brought it here to the Earth, then over here at the edge is where Pretoria and Johannesburg would be. This thing, if we dropped it here on the Earth, would cover a good part of South Africa. This huge crater at the top is where the volcanic material comes out. And we have space missions orbiting Mars. We can look at this close up with our space missions. Here's the cliff up on the crater at the top. You can see a landslide right here where it's slumped and the sand has fallen down into the crater. The height of that crater wall at the top of Olympus Mons is the size of the Drakensberg here in South Africa. You go to KwaZulu-Natal and you look up into the facade of the Drakensberg, looking up into Lesotho, those gigantic mountains are only as big as that little tiny rim of the crater on top of Olympus Mons. Why is this mountain so big? Mars has got volcanoes, but it doesn't have continental drift. Here on the Earth, the interior of the Earth is hot. It's 6,000 degrees Celsius. That interior heat is produced by radioactivity, primarily radioactive krypton. And that came out of stars that exploded billions of years ago during their lifetimes and produced radioactive material that then became part of the Earth, radioactive potassium, which has the element K. That radioactive potassium heats the inside of the Earth, and that drives continental drift and pushes our continents around. So when a big volcano forms, it only lives for a while, and then the continent or the volcano gets pulled away from the hot spot and a new volcano forms. On Mars, it's too small. There's not enough heat. There's no continental drift, and this volcano just grew and grew and grew. Here's a picture taken by Mars Orbiter, which took a picture. Look at the parachute right here. This is a few years ago. That parachute was dropping a little car down onto the surface of Mars. That car's name was Curiosity. And it's been driving around on Mars ever since for years. There's a picture it took of a mountain on Mars. That white you see is snow, but the snow on Mars is frozen carbon dioxide. It's dry ice, it's not water ice. Temperature gets very cold in the winter. That little car driving around's left tracks. There are the tracks of Curiosity. And in the distance, look at this. You're familiar with these here in Mahaking and up here in this part of the country. It's a dust devil, just like we get here when it's hot. Mars has got dust devils. And in this amazing picture taken by Mars Orbiter looking down on Mars, you see the big crater here on Mars. All these little stripes you see running across this picture are dust devil tracks. Mars is just covered in tracks from dust devils. It's very Earth-like. In the summertime at the equator on Mars, temperature gets up to 20 degrees Celsius. It's about the temperature here in this room now. It's Earth-like temperature. But at nighttime, it drops to minus 150. And the atmosphere is thin and it's carbon dioxide. It's not a good place to live now. It's a little bit too far from the sun. But Mars wasn't always like that. Mars has had running water. Maybe Mars has life, and I want to talk to you about that. But first, I want to show you a video. This video, 2 weeks ago today. 2 weeks ago today, NASA and the Jet Propulsion Laboratory dropped a new car down onto the surface of Mars. Its name is Perseverance. Mars missions often fail. It costs several billion US dollars to send a mission to Mars. So let's say $3 billion is 60 billion rands to send a mission to Mars. Sometimes they crash into the surface. Sometimes they miss the planet. Sometimes they just fail. This often doesn't work. If you work in space science, it's so exciting, but you will spend years or decades of your life building a mission, and then somebody puts it on a rocket and they light the rocket, and you know yourself, rockets sometimes explode. This is really tense, but then your rocket goes. Your satellite orbits and it goes out to Mars. It takes 8 months to get there. And then it goes into orbit about Mars, and then you drop a mission from that down onto the surface of Mars with a special little rocket, a sky crane that can hold the little car and drop it onto the surface. 2 weeks ago, let's watch it happen.
We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground.
Indicate chute deploy.
This is not computer animation.
Navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration in the velocity. Our current
That parachute is 20
velocity
meters across.
150 meters per
Atmosphere
second
of Mars is
at an
very
altitude of
thin.
about 12 kilometers from the surface of Mars.
Heat shield set.
Perseverance is now.
So that was to keep it from burning up. They've now released that. It's just falling onto the surface.
This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second.
145 meters per second.
9.5 kilometers above
500
the surface.
kilometers per hour. If this thing doesn't slow down, it's going to crash. We are about to land on an alien planet.
Nav filter converge. Velocity solution 3.3 meters per second. Altitude 7.4 kilometers.
Now has radar lock
Now
on
we're
the
down to a
ground.
reasonable
Current
speed.
velocity is about 100 meters per second, 6.6 kilometers above the surface.
But if you land on one of those cliffs, you're going to crash and destroy your mission.
Perseverance is continuing to descend on the parachute.
You've got to land
We're
somewhere
coming up
smooth.
on the initialization of terrain relative navigation, and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
The computer has to do that. The people who are controlling from the Earth, the time travel to Mars
That the
for the radio signal is about 20 minutes.
A valid solution and part of terrain relative navigation.
So the computer's controlling the landing. The humans can't. They'll be too late.
We have priming of the landing engines.
Look at the sand dunes. Boy, do we know those here just to the north in the Kalahari Desert.
Current velocity
Mars has lots of sand
meters
dunes.
per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface.
They're down to 100 kilometers per hour now. That's still a bit fast for landing.
Constant velocity accordion, which means we are conducting the sky crane.
So on the left, you're seeing live from the mission itself, the sky crane here, which has the jets that are raising that dust on the right. And there's the car to be landed right
20
there.
meters off the surface.
Nobody yet knows if this is going to work. It often fails.
We're getting signals from MRO. Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
Would you like to be a space scientist and do something like that? How exciting to actually land a car on another planet. Now here, when the car was being built, here it is in the laboratory. You can see a person here. It's kind of the size of a car here on the Earth, but it cost nearly $3 billion US. Here it is on the surface of Mars taking a selfie just 2 weeks ago when it landed. There's the front wheel, there's the surface of Mars. This thing is high-speed technology. For $3 billion, how fast can your car go? This thing goes at top speed, 4 meters per hour. Let me let you digest that, 4 meters per hour. Why is it so slow? Well, imagine for yourself. The controller on the Earth is watching 24/7. Somebody's always watching this thing. But the time it takes a radio signal to go to Mars and come back again is typically about 20 minutes. So now I want you to imagine, you're out on the road here, mahakking, you're driving to work. You're driving 60 kilometers per hour. Somebody pulls out from in front of you and you hit the brakes and nothing happens for 20 minutes. You can't drive 60 kilometers per hour. 4 meters per hour, because if something happens, this thing has got to protect itself. You don't want to hit a rock, you don't want to fall off a cliff and lose your $3 billion automobile. So it's very slow to drive around. But there's a picture from space taken by an orbiter. There's the bit that was protecting it from heat, hit the ground. There's the descent stage. There's the little car itself. There's the heat shield over there. They all fell in different places. And there's one of its first pictures when it landed on the ground. It's called Perseverance. People working on it give it the nickname Percy. And there it's taking a picture of the surface, but it's got a little camera on it and it's got another little mission on it. And the little mission's called Ginny. This is not a real picture now. This is still a computer animation. Ginny is a helicopter. We've never done this before. Mars has got such a thin atmosphere that Ginny's rotor blades are 1.2 meters across. The mission itself is about the size of a tissue box. It weighs 1.8 kilograms. The rotor blades are made out of carbon. They have to be very light because the atmosphere is so thin. And in about 2 months' time, this little helicopter for the first time is going to take off and see if it can fly around another planet. We've got other places we'd like to do that. This is a test. So watch the news. Within a couple of months, we hope Ginny's flying and she'll be flying around on Mars and taking pictures all over the place. Well, here's a picture of Mars and you'll see coming out of this crater, these are water valleys. Water has run on the surface of Mars in the past. It probably hasn't run for the last 3 billion years, but it did run on Mars. Could there be life on Mars? Some people think so. 100 years ago, people believed that there were Martians. More than 100 years ago, The French author Jules Verne wrote a book called War of the Worlds, where the Martians, because their planet was drying up, you can see how dry it is, look at this picture, they decided to escape Mars and come to Earth and conquer Earth and kill all the humans. And that made this science fiction story, War of the Worlds. And people believed in Martians. Some people still do. There's a feature on the surface of Mars, which is known as the face on Mars. Here's an old picture of it. And some people were claiming, oh, the Martians actually built this as some sort of monument. They didn't. Here's a close-up picture over here. It's an odd-shaped mountain indeed, but it's a natural mountain. It's geological. But that doesn't mean there isn't life on Mars. Did the Martians build a happy face? This has a crater which just happens to look like an emoji. But here from Earth is an electron micrograph, a close-up picture at microscopic level of an asteroid that came from Mars. Now there you should ask yourself, an asteroid came from Mars? How do you know that? Somebody's walking along. Here in Mahakeng, they go out and walk in the game reserve. And there on the ground is a rock and they pick it up and say, oh, wow, look at that. Must have come from Mars. Hey, who can do that? Well, first of all, if it fell from space, the surface gets melted and you can see that it's a meteorite that fell from space. But how do you tell it came from Mars? We've got a couple dozen of these rocks. They're very rare. There are gas bubbles trapped in the rocks. So something smashed into the surface of Mars, knocked some rocks free that then orbited around the sun. And then some of those rocks fell to the Earth, and the gas bubbles trapped in those rocks have got the atmosphere of Mars, not the atmosphere of the Earth. You can chemically identify this rock came from Mars. And what you're looking at here in this electron micrograph are what look like fossil bacteria to some people. Could there be bacterial life on Mars? What an interesting question. Here on Earth, most life here on Earth is bacterial. All right. We think the big mammals like us, the lions, the elephant, the buck, we think those are the dominant life forms. But the vast majority of the biosphere here on Earth is bacteria. And deep in the mines, not far from here, in the Witwatersrand, 2 or 3 kilometers underground, there's life down there. There's bacterial life. And it lives off the interior heat of the Earth. It doesn't need sunlight. Could there be bacteria like that on Mars? And if there are bacteria like that on Mars, did they form independently from here on the Earth? If life formed twice on 2 different planets, then we know that life will form commonly in the universe. And so we would like to discover bacterial life on some other planet and see if it's got DNA just like here on the Earth. Well, maybe an asteroid knocked some life off the Earth and made it form on Mars. Maybe it formed first on Mars, and a big rock knocked something off Mars and that seeded life here on the Earth. Maybe we're Martians. What interesting questions. Let's see if we can find life on Mars. That's one of the things Percy's doing. Percy is going around and drilling into the ground on Mars and dumping little pellets like droppings, not out of the back of a buck, but out of the back of this little mission. It's dropping these little pellets on the surface of Mars, and then a future mission will go there and get those and bring them back to Earth to analyze them, trying to find life on Mars. Now let's go farther out in the solar system. This schematic, that little dot in the middle is supposed to represent the sun. This is, of course, is not to scale. And then the orbits of Mercury, Venus, Earth, and Mars. Between the orbit of Mars and the giant planet Jupiter is the great asteroid belt. And the asteroids are out there by their thousands. Some of them are gigantic, tens of kilometers across, and some of them cross the Earth's orbit. They crash into the Earth occasionally. This one is called Bennu. It's 500 meters across. And just last year, a space mission landed on the surface of this little asteroid and scooped up part of it and took off again. And in a few years' time, it will come back here to the Earth, and we will analyze in the laboratory the chemical composition of this asteroid. If that thing crashed into the Earth, which is possible, it will explode with the power of vast numbers of hydrogen bombs. It will cause a major explosion. This happens. Here in Russia in 2013, the Russians now, in Russia, I go to Russia almost every year. I lecture on a private train there and I do trips in Russia. I've done Trans-Siberia and I go up to the Arctic Circle in the winter. The Russians all have got dash cameras on their cars because there are lots of automobile accidents in Russia. And whenever there's an automobile accident, it was of course the other driver who was at fault. You know that here too. If there's an accident here, it was the other person. So they've all got dash cams. And this is live. Somebody just driving around in their car, and look at this thing coming in from the upper left. This is an asteroid entering the Earth's atmosphere. It's burning up, it explodes. It released 20 times more power than the atomic bombs that were dropped in World War II. Another dash cam, here it comes. It missed the city of Chelyabinsk, but not by much. And so there was a big explosion. People saw the flash of light, and they rushed to see, what's this light? And it took some time before the explosion arrived. But many people have got their cameras running. These guys will walk out to see what the flash is. She's watching her colleagues. They've gone to the window to see what the flash is about. The explosion's coming. And because it broke into pieces, there are multiple explosions. And you'll see they decided it would be better to just get out of there. Young couple having a chat up in the office instead of working. And their chat up is interrupted here. Schoolroom. And here's a job interview. I know you deans were doing a job interview here on campus yesterday. Imagine if during your job interview this happens. This thing has exploded with 20 times the power of the World War II atomic bombs that ended World War II. This happens to the Earth. There's where it crashed through the ice. They got the remnant to it. Back in decades ago in the US, over New York State, another one came in. This was called the Peekskill meteorite. This is very rare, but this one hit something. There was a young woman, 18 years old, who had just bought herself a new car. It was a very old car. She only paid $300 for it, but she had just got it. And this thing hit her car. It crashed right through the boot. There's the rock right there. Smashed through her boot. She's only 18. It's her first car. It was her $300 is all she had. She spent all her money on it. Don't feel too sorry for her. She sold the car for $25,000. She sold the meteorite for $50,000. She was rich. You might hope this happens to you as long as it hits the boot and doesn't get you. So she profited from that. I want to show you what one of these explosions is like. This is terrible what we're about to watch. Until the 1960s, Russia and the US primarily, but other countries too, France, exploded atomic weapons in the atmosphere, testing them. This is an atomic blast. It's a test, which is only about twice the size of the World War II atomic bombs. It's 10 times smaller than the Chelyabinsk meteor you just saw. This is in the Nevada desert. This is a gigantic mountain down there. And here comes the test with the explosion. We have to get rid of these weapons. If anybody ever uses one of these in anger again, it's a disaster for the entire world. That blast is coming at 300 kilometers per hour. There's no outrunning it. It's sweeping up everything in its path. Anything there that can burn is going to be set on fire. And of course, there's radioactivity. And the only reason I'm showing it to you is this is just to compare with what naturally happens with these explosions. Here's a map of the Earth, a Mercator projection. Here's Africa. This is over the last few decades, and each of these dots represents an explosion of a meteor hitting the Earth. There's Chelyabinsk, this great big red one up here. Hiroshima was only 20 kilotons. It's one of these little yellow ones here. Look at all the hits we get. Of course, mostly they hit the ocean. The Earth's mostly ocean. If they do hit the land, a lot of them hit Russia, but that's just because Russia is the biggest country in the world. And here's an example over the last 30 years. We get hit every couple of months by something that's got the equivalent half a ton of TNT explosion. Every 2.5 years by something that's 10 kilotons. Every 5 years by something that's as big as the Hiroshima bomb. And then occasionally something like Chelyabinsk, 440,000 tons of TNT explosion. 65 million years ago, the Earth was hit by a rock, not quite as big as the one that made the Frida Fort crater, but one that made a crater 180 kilometers in diameter. The rock that hit was only 5 to 10 kilometers in diameter, but it exploded with the power of 100 million megaton hydrogen bombs. It vaporized the ground, it vaporized the oceans, it blasted dust, smoke, water vapor into the air. This happened off the Yucatan Peninsula in Mexico. This is the United States. Here's Texas, where I studied as a PhD student. There's Florida. This is the Yucatan Peninsula of Mexico, Gulf of Mexico. It hit right there. We study that crater now. It exploded with such power and such heat that North America, the United States, burnt to the ground. Everything was set on fire. The tsunami crossed the Gulf of Mexico and traveled more than 1,000 kilometers inland, and we can pick up the debris from the tsunami 1,000 meters from the coast now in Texas. The shock wave traveled around the world and set fire to what was to become India. At that time, India was an island off Madagascar, still because of continental drift, drifting towards the Asian continent. India was set on fire too. And dust, gas filled the atmosphere. The world turned dark. It turned dark for 10 or 20 years, and death came. The plants died. 75% of all species were driven to extinction. And of course, the ecosystems here on Earth were dominated by these gigantic animals, the dinosaurs. There were mammals around. Our ancestors were here. They were tiny little furry things that didn't come out during the day, because if they came out during the day, one of these big guys would eat them. They just skulked around and hid in the bushes. But what happened when the asteroid came? The atmosphere filled with smoke and with dust, and it got cold and the plants died. And these big dinosaurs couldn't get enough to eat, and they died. The little mammals made it through. They had fur. Some of the dinosaurs made it through. The ones with feathers, they're still with us. They're called birds. The birds are dinosaurs. They're the ones who made it through the Cretaceous extinction. Here from a cartoonist named Gary Larson is his view of what happened at that time. Here are these big, tough dinosaurs. And it's getting cold. The sunlight's been blocked out, and the snow's starting to fall, and they're not going to make it through. Here's this stupid little furry mammal, and it's got enough fur, and it doesn't need much to eat, and it made it through. This is our great-great-granddaddy or great-great-grandmama. That's our ancestor who made it through. And if you could have been here 65 million years ago, here in South Africa, we've got the fossils. These ecosystems were dominated by dinosaurs, mammal-like reptiles, and the asteroid wiped them out, and that gave us our chance. It will happen again. There's nothing to stop it. We will have impacts like that again. I'm now taking you farther out in the solar system. Here's the big planet, Jupiter. Jupiter is bigger than all the other planets added up. It's so big it has no solid surface. It's made out of primarily hydrogen and helium, as Cecilia Payne showed us the universe is back in 1925. So this is a gas and a liquid planet made of hydrogen and helium, but with some methane and ammonia mixed in, and it has great storms. This is called the Great Red Spot. You can see that with the telescope here on the campus of Northwest University. If you haven't seen it, ask Professor Madupi to show you Jupiter sometime. It's up in the morning right now, and through that telescope with your eye, you can see this great red spot. It is a hurricane. If I get my cursor to come back here, no, maybe it'll come back. It's a hurricane that has been blowing now for at least 300 years. What happens here on the Earth? Big storm comes, like just a few weeks ago, off of Mozambique. You remember the big floods, and then it came, and you had loads of rain in the high veld. But when a big storm here on the Earth gets over the land, there's no more water to be pumped into it by the heating of the ocean, and it dies out. Jupiter has no land. And that big storm right there has been blowing for at least 300 years. It's bigger than the planet Earth. The wind speeds in that storm, 600 kilometers per hour. Sorry, I need to go back. This is a beautiful close-up view of the atmosphere of Jupiter taken by a mission called Juno that is orbiting Jupiter right now. The colors are a little bit saturated, but look at the incredible turbulence. There is a storm down here, smaller than the Great Storm. Here's another one up here, and incredible winds and turbulence in the atmosphere of Jupiter. Besides the science, these things are great natural works of art. If you're interested in astronomy, you might like something like that as a poster to put up in your home. Here's a picture from a mission that was orbiting Jupiter many years ago, and here are two of Jupiter's many moons. One is called Io. It's the size of the Earth's moon. This one is called Europa. It's also the size of the Earth's moon. When I was a student in the 1970s, before this mission took this picture, Voyager, we thought the moons of Jupiter would look like the Earth's moon, just covered in rocks and craters and no atmosphere. Boy, were we wrong. We got there to discover Io looks like a cosmic pizza. It's so close to Jupiter that Jupiter's raising tides in the rock on Io, and the friction, rub your hands together, you feel your hands get hot? The friction from the tides on Io have melted its inside. It's covered in live volcanoes. This is the biggest in terms of diameter volcano in the solar system. We call it Pele, after the goddess of volcanoes from Hawaii. And there you can see the edge of the crater. Here's a lake of molten sulfur up here on the corner. Is molten sulfur black? No, molten sulfur's red. You've seen sulfur here. It's kind of the color of a match. So why does that lake look black? And that's because lakes reflect the sky. If you stand on a lake, we got a lot of rain right here. There's a lake just over the other side of the fence from the observatory. Stand on the edge of a lake on a nice sunny day like this, and you'll notice the lake's blue. Go up to Lake Malawi. Oh, Malawi's such a wonderful country. What a wonderful lake. You stand on the edge of Lake Malawi and you look at it, and it's this clear blue lake. Why is it blue? It reflects the blue sky. Io is the size of the Earth's moon. It has no atmosphere. So if you stand on the edge of this lake right here, it's reflecting the sky, and the sky's black. If you could stand on the edge of that lake, you'd see the stars reflected in the surface. It just acts like a mirror. We even saw volcanoes erupting as we flew by Io. There's a volcano going off live right there on the edge, and boy, you should have heard the excitement when they saw that for the first time. Well, I want to take you out to the most important moon of Jupiter. This one's called Europa. And Europa is a little bit farther from Jupiter. It's covered in water ice. And the water ice is cracked. This picture is only a few tens of kilometers across. Look at the cracks and look at the different color. The tides of Jupiter have cracked the ice, and underneath that ice, water has come up. This moon has got an ocean, maybe 25 kilometers deep underneath that ice. Let's go there and look for life. I want to show you something here on the Earth. When I was a student at university, as an undergraduate, San Diego State, I was studying biology. I wanted to be a marine biologist. I grew up in a coastal town. I love to skin dive, I love to surf, I love to swim in the sea. It's one of the reasons why I've moved to Port Alfred here in South Africa. Port Alfred now is very much like San Diego was in 1880. I'm going back to what California was like 150 years ago. It's wonderful. So I can go kayaking, I can go swimming. I still love the sea. Marine biology. But here on the Earth in the 1970s, deep in the sea were discovered some things that were called black smokers. You can look them up on the internet, but I have to warn you, if you put into Google black smokers, you get health sites for African Americans. You need to put black smokers vents in the sea, and then you'll find that deep in the sea, there are these volcanic vents. We're now going down under the ocean with another kind of exciting science. This is a deep sea submersible that's going to go
We have to be careful
kilometers down into the ocean off the Galapagos Islands, off of Ecuador. Here's a black smoker.
Wow.
A volcano is gushing out water,
All right, guys.
300 degrees Celsius. That deep in the ocean, the surrounding seawater is 2 degrees Celsius. And the water mixes to where it's a nice temperature.
Looks like a little beehive.
And there are bacteria that can live off of that black smoke, those minerals coming out. And then there are animals that can live off the bacteria and plants.
Discovered.
I'm going to skip forward just a little bit here. Look at the crabs.
Up above.
Look at the shimmering from the hot water.
Sample. Let's just take a good look at it.
Some biologists think this is where life formed here on the Earth at these deep sea vents. Maybe.
Albanellids there. Albanellids.
But maybe Europa's got vents like that. Jupiter is stretching it like it stretches Io. It's got a warm ocean underneath. It's cracking the ice. Maybe there are hot water vents there. We would like to send a mission to Europa, drop down on the surface, and then with a nuclear reactor, a little one, we'd make the mission hot so it melts the water, the ice, and then it would just sink through the ice until it popped out into the ocean, and then a little swimmer would go out with a camera and look for these events, these vents. Maybe things live on Europa. There's a place to look for life. Now that has to be everybody's favorite planet besides the Earth. Don't you just love Saturn? With its great rings, What an amazing planet. It also is a gas giant. It's smaller than Jupiter, but it's very much bigger than the Earth. These rings, 137,000 kilometers out from Jupiter. What are they? Millions upon millions of tiny little moons. Just millions of moons all orbiting about Saturn. And this picture from the Cassini mission, which orbited Saturn for 13 years, you can see right through the rings. Look how thin they are. Get up close with Cassini and you can see one of the tiny moons of Saturn sculpting these tiny little rocks in the rings into waves. There's an artist's impression of what it would look like if you got into the rings. These tiny little moons are typically the size of your head to maybe the size of a house. And they're not permanent. This comes from a moon back when Saturn was young, drifting too close to Saturn, where the tides from Saturn actually shattered the moon and tore it apart. And they won't last forever. They will eventually dissipate. So the Saturn's rings are temporary. We're lucky to be here at a time when we get to see them. Up at the pole of Saturn, there's an incredible storm. The storm's thousands of kilometers across, and it's got a hexagonal size to it. We never guessed that would happen. Now that we've seen it, we can explain it, but we didn't know it would happen. We didn't predict it. And down deep in that storm, here's a huge hurricane blowing. This one's a couple thousand kilometers across. Wind speed's about 600 kilometers per hour. And so here's a chance for somebody who studies weather here on the Earth, a meteorologist, to look at meteorology under much more extreme conditions to try to understand better weather here on the Earth. Saturn has a moon named Enceladus. It's only 500 kilometers across. And we thought Enceladus would just be a frozen rock. It's not. Something heats it. We don't know what. But down here in the southern hemisphere, these cracks, we call them the tiger stripes, are where Enceladus has been cracked. It's broken. And out of those tiger stripes are shooting water geysers. And with our spectroscopes, we've been able to tell that's seawater, that's salt water coming out of there. Enceladus has got a saltwater ocean. Somehow it's heated inside. Maybe there's life there too. There's another exciting possibility. There's a moon around Saturn called Titan. It's the size of the planet Mercury. And way out at Saturn, 10 times farther from the sun than the Earth is, it's got an atmosphere. It's got a thick atmosphere. And we dropped a mission down into the atmosphere of Titan about a decade ago. Here are the pictures from a real mission dropping down onto the surface of Titan. It's got rivers. There's a river valley about 30 kilometers long. Let me tell you that the surface temperature on Titan is minus 180 degrees Celsius. That's not running water. The atmosphere of Titan is hydrocarbons, methane, ethane. The rivers and the lakes and the oceans on Titan are made out of liquid hydrocarbons. Well, here on the Earth, liquid hydrocarbons, we call that oil. That's what we're running our economy off of here. That's what the atmosphere of this thing's made out of. This picture was taken by a state-of-the-art camera. Expensive, $3 billion for that mission. The camera was designed 5 years before the mission was launched. The technology was locked in. The mission then took 10 years to get to Saturn. By the time it got to Saturn, the thing that you've got in your pocket, there's a phone I've got. I'm using it just for timing this. Come back. There we go. You've got a phone, right? I'm glad you're not using it right now. The camera in my phone has 12 megapixels for the camera. The camera that took this picture you're looking at, 95,000 pixels. It was the best camera that could be built when the mission was launched, but by the time it got to Saturn, you had something in your pocket that was vastly better. If you think back to those moon landings, 1969 to 72, all of the computing power that NASA had at hand to send people to the moon was vastly less than you carry around in your pocket with your little phone. Your computer is much bigger than all the computers that existed back at the time of the moon landings. Technology is fantastic. Maybe young people who are listening to this, you're going to be in technology, information technology, computing, you're going to build things like that. And of course, our machines get more and more amazing. Titan's got sand dunes. Look at the sand dunes. This is Titan, this moon of Saturn. But that's not rock sand. Water ice on Titan is so cold, it's as hard as rock, and it breaks up into little chips and it blows in the wind. And those dunes that look so much like Earth dunes are dunes not of silicon dioxide, not quartz like here on the Earth. Those are dunes of little chips of water ice. What an alien place. Well, here's an amazing picture. This ranks as one of my favorite pictures in all of astronomy here on the left. From the Cassini mission, there's Saturn with the sun behind it. The mission's out beyond Saturn, looking back into the inner solar system. And this is not photoshopped. That little dot right there is us. That's the planet Earth. So when you think about we humans are changing this planet Earth, you think of it as something big. It's this tiny little pale blue dot floating in space, delicately balanced between the fire and ice and the solar system. That's us. Just for amusement on the right here, we have another mission that's orbiting the planet Mercury in close to the sun, and it turned around and looked back into the solar system. There's the Earth and the moon as seen from Mercury. Just imagine how tiny we are. Just another fun moon I like. We're getting near the end of the solar system now. This one's called Miranda. It's only 500 kilometers across. It orbits the planet Uranus, and when it was young, it was smashed by another giant rock that almost broke it to pieces. Now, the outer solar system, there's a lot of water, and it's all frozen ice, and there's a cliff right here on Miranda. I'm going to blow it up. There's that cliff. If you, like me, are interested in mountain climbing, if you're really serious and you'd like to try mountain climbing in the winter in the cold climates, some people like to climb ice. That ice cliff right there is 20 kilometers high. It's 2.5 times higher than Mount Everest. There's the greatest ice climb in the solar system. But the gravity is very low. Undergraduates, you have an undergraduate physics student, as many of us in here who teach that do. Even in the first year, we can teach them, even in high school, we can teach them to calculate how fast would you get going if you were climbing that cliff and you fell? And the answer is if you fall 1 kilometer and land on a ledge, you're not even going to hurt yourself. If you fall the whole 20 kilometers, you're in trouble. But that's a nice calculation. For those of you who do teach, there's a calculation. Have your students calculate what would happen if they fell ice climbing on this giant ice cliff of the little moon Miranda. The farthest planet in the solar system is Neptune, 4 times bigger than the Earth. It's got a great storm, or it had a great storm. It's now disappeared, much like the one on Jupiter. And Neptune has a wonderful little moon called Triton. And here from the Voyager satellite is the planet Neptune with its little moon Triton right here. Triton's tiny, it's smaller than the Earth's moon, but we got some close-up pictures of it. And there it is. Triton has seasons. In the southern hemisphere here, it's summertime. And what you're seeing is nitrogen. Mostly what you're breathing right now is nitrogen. Here, the nitrogen is being vaporized and it comes out as geysers that blow away in the wind. These black streaks you see are contaminated nitrogen blowing out of nitrogen geysers, because in the summer on Triton, out that far from the sun, it warms up to a balmy minus 235 degrees Celsius. And at minus 235, the nitrogen vaporizes and makes an atmosphere. And the gas floats around to the winter hemisphere up here, where it's minus 238, and it's so cold the air freezes and just falls to ground as snow. So the very air just freezes out and makes this terrain up here. We call it spawn-spec terrain. It looks like a melon. Well, some of you are young enough, you're still going to be with us in 80 years. I'm probably not here at that time. But 80 years from now, when the seasons flip, I say it'll be summer up here and it'll look like that. It'll be winter down here, it'll look like that. Keep that in mind for those of you who are going to live another 80 years. And remember, I told you that late in life when you can look at that. So the farthest in the solar system is something we used to call a planet, Pluto. Pluto's no longer a planet. How sad. It used to be the 9th planet in the solar system, but no longer. Why? We sent a mission called New Horizons past Pluto, and it's tiny compared to the moon. It's only 1,200 kilometers across. The moon's 3,700 kilometers across. This thing's tiny compared to the moon. And so we just decided not to call it a planet anymore. But close-up pictures, there are mountains on Pluto. We flew by, we got pictures. This is really Pluto. The mountains are up to 1,500 meters high. Spectacular pictures. It's even got an atmosphere. Why did we demote it? Because in my childhood, we had the planets of the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. We didn't keep Pluto because it's so much tinier than the other planets, and because there are thousands of things like Pluto out beyond Neptune. Here are some of the ones we've discovered. We call them trans-Neptunian objects. And there's Pluto with its 5 moons: Eris, Makemake, Haumea, Sedna, Quaoar, Orcus. Do you want to have your children or grandchildren having to learn the names of the planets of the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto, Eris, Makemake, Haumea, Sedna, Quaoar, Orcus, and on through hundreds or more we're going to discover. These things are out there by the thousands. And so we call them dwarf planets now, and Pluto's just one of the biggest of the dwarf planets. They come in funny shapes. Here's the last one I'll show you. It's called Arrokoth. And you can see two of these little dwarf planets actually crashed in and stuck to each other. They're probably glued together by ice. This thing's only 30 kilometers across. And what a quaint little object orbiting out there beyond Pluto. Well, the most important object in the universe to us, our beautiful blue planet, the Earth. That question I asked at the beginning, are we the only ones in the universe who can think about this? Is this the only planet with life? We hope not. We found 4,000 planets around other stars, and I will do another public talk here at the university, probably by Zoom again sometime in the future, where I'll talk about those missions because I work on that with the satellites that are looking for those. In order to understand whether there's life on those other planets, we needed to understand life here in our solar system, and that's what you and I have been doing today. But I also want you to appreciate how delicately balanced the Earth is between the heat of the inner solar system and the runaway greenhouse effect, Venus unlivable, and just a little further out, too cold, Mars unlivable. What's the future of the Earth? I'm going to leave you with a bit of a sad thought. Just as for us and for every living thing on this planet, we're born, we lived, we die. That happens to stars and that happens to planets. They're not forever. This is an artist's impression of what we know is true. I'm a stellar astronomer. Professor Madupe is a stellar astronomer. We understand the stars, we understand them well. And we know that our sun, as it fuses hydrogen to helium, is using up its fuel, and that is making it grow bigger and brighter. It's swelling up to become what will be a red giant. In just a couple billion years, in this artist's impression, the sun will become so big and so bright, the oceans will boil, the atmosphere will fill with water vapor, we'll have a runaway greenhouse effect like on Venus, and life on this planet as we know it will no longer be possible. Maybe the bacteria down in the mines might survive that, but ultimately the sun will swell up until it comes right out to the Earth. It's going to vaporize most of the Earth. Maybe a little rock will be left behind. And then when the sun dies, it will collapse to where it's only the size of the Earth. It'll be a density of 1 ton per cubic centimeter, and it'll fade away as something we call a white dwarf, and there'll be no light. And if there's anything left of the Earth, it'll just be this tiny little cold rock. Nothing is forever. And so what I want you to do with this is I want you to appreciate how precious our Earth is and contemplate that we 8 billion humans are changing it, perhaps not always in the best way. And through your careers, and I hope with this excitement of this, you decide, in my life, if you're young now and you haven't chosen your career, I'm going to do something in science, technology, information technology, computer. I'm going to make something happen. I'm going to have the excitement of discovery. The life of a scientist is fantastic. Thanks for listening today, everybody. And those of you out there by Zoom whom I can't hear right now.
Thank you, Prof.
Would you like to sit?
Yeah, let me. Thank you. Thank you very much, Prof. Don, for a wonderful, exciting lecture. We've learned quite a lot of beautiful, amazing facts, journey through the solar system. I think maybe we should ask Prof. Francois to handle the question and answer session. So we're opening the question and answer session to everyone in the audience. Feel free to ask questions, please. Yeah.
Thanks for that amazing, inspiring talk, Don. It's really a privilege to listen to you and to learn from your experience as a scientist. Just maybe to introduce, before I give options for questions, to me it was, as a bioenergeticist, it was very clear how a central role energy plays in all of this. So maybe first question is to ask you about the role of energy in all of this, in the universe and our maintenance of it.
We probably have to keep swapping back
Yeah,
and forth
sure.
here so people can see this. Let me just ask, Leandra, can you bring the screen up full screen so that we're no longer looking at the slides? Should I stop screen sharing? Let me stop the screen share here just a moment. And there maybe we can bring this up so that we've got full screen like that. So I don't, for those of you out there on the webinar, Leandra, if you could just see if we can get for the question session, so we're showing. So you've asked me about energy in the universe.
Yes.
And as I said at the beginning, I'm going to shift over here just a little bit, so I'm also looking partly at the camera as I talk to you, Francois. So I'm talking to Francois to my left. I'm looking at the camera for those of you out there on Zoom. I'm speaking to you. We hope to control hydrogen fusion, which is the main power source for stars in the universe. There are more extreme energy sources that we are not going to gain control over, but boy, do they produce amazing effects in the universe. Gravity is the ultimate force in the universe. Gravity is weak compared to everything else, but you can't beat gravity. It's always there and it's always waiting. It eventually will make the sun become what we call a white dwarf. For really massive stars, they collapse to be even neutron stars, where you have something with the mass of the sun and it's the size of Monkey King, or even black holes. And we now know that when neutron stars crash into each other, they produce elements like gold and silver and mercury and a lot of the things we run our economy off of. The elements heavier than hydrogen and helium, for the chemists in the audience, the elements heavier than hydrogen and helium have been cooked up inside stars, which either blew them away as winds out into the universe, or exploded as supernovae, or crashed into each other and contaminated the gas of the galaxy, so that when the sun formed 4.65 billion years ago, 2% of it was heavier material than that hydrogen and helium that Cecilia Payne discovered in 1925. And that 2% is currently partly you and me. Except for the hydrogen in your body, the rest of you, your atoms were cooked up in stars. And that energy source is phenomenal. We're never going to control that. Gravity is too much for us. But we do have control of the power of the stars now, and we're hopefully going to, that's the ultimate energy source. So when somebody out there says to me, the dean or the VC says, what good is astronomy? I have to answer, the payoffs come, but they take a long time. It took us 400 years to understand the stars and gain control of the energy. And let me give one other example of that. Your camera in your phone uses a technology that we astronomers developed when I was a student in the 1970s. Two groups were developing the technology that later became the things that are the chips in our phones and our TVs and our computers, astronomers and the military. And the military keeps everything secret. So industry got all of that from astronomy. And we don't charge. The world is good to astronomers. Those of you who are taxpayers, your tax funding comes to us, and it's my pleasure to talk to you, but you paid for that. You've paid for that my whole life. And I get to use amazing machines, expensive satellite missions and giant telescopes, and the public pays for that. And we scientists have a duty to tell you about it and to talk to you. I got off track on the questions.
Thanks for that.
Let me just tip this back towards you this way.
Perhaps we're going to look at the quick Q&As here on, let's swap between the panel here, or the audience here, and the questions on video. Let's just have a look if there's any questions here. Okay, there's questions from Tulani Jill. Don, can you maybe read that and respond to that, please?
Okay, let's see. Tulani, is there any chance that the Earth, of escaping the red giant stage by expanding its orbit outwards? Thank you for that question. I love that question. Tulani, I was part of a group where we discovered a planet around another star about 10 years ago. And that star is much like the sun. And we calculated that as that star becomes a red giant, it will blow away a wind and lose enough mass that its planet, which is currently at the same distance as the Earth, will drift away and then survive, not being utterly vaporized. But it's still going to be, the atmosphere is going to be blown away and the rock's going to melt. And so if you mean by survive, there's a chance that the Earth will survive the red giant stage, but it will survive as just a dead rock. And I hope that's made you feel better. Now I see another question here from Hendrik Bowman. Says, I'm still upset that Pluto's not considered a planet anymore. For decades, it's been a science cultural icon. Who killed Pluto? Well, the answer to that is many people Hendrik, but I have to put my hand up. Let me answer that. Pluto, well, the first planet that was ever discovered, humans have known about Mercury and Venus, Mars, Jupiter, and Saturn since time immemorial. Your ancestors here in Southern Africa knew those planets. Since humans are conscious, we knew those. The first planet that was knowingly discovered was the planet Uranus, and was discovered by an English astronomer named Herschel. And then astronomers predicted, because this planet Uranus wasn't moving exactly as it should, according to gravity, there should be another planet. And in the 1800s, they predicted and found Neptune. That was very exciting. And so in the 1900s, people were looking for more planets. And an American astronomer who was young at the time named Clyde Tombaugh in 1930 discovered Pluto. He was famous for that. It was Clyde's claim to fame. He was a wonderful man, and all astronomers who ever met him loved him, and nobody was going to take Pluto away from Clyde. And he kept living. He lived and he lived and he lived. He was almost 100 when he died. But once Pluto died, we had to take the situation in hand. And the answer is, it's the International Astronomical Union who the world gives the right to do things like decide on calendars, time, naming planets, naming craters, naming stars. And we chose to demote Pluto to be a dwarf planet because it's so different from the other outer planets and because there's so many other dwarf planets around. And so I kind of feel like that too. And in my childhood, Pluto was a planet. I kind of miss it being a planet, but you've got all these other wonderful little Pluto-like things out there. And look at what you just saw of Pluto now. Back when it was a planet, it was just a little dot in the sky, and I just showed you pictures of mountains on Pluto. That was science fiction until a couple of years ago. How wonderful. Let me see if there's some more here. What is the probability? So this one's from James Chibueze. James says, what's the probability of finding a planet hosted by a massive star greater than 8 solar masses? All right, James, let me just fill the audience in. Massive stars, more than 8 times the mass of the sun, are rare, but yes, we potentially can find planets around them. Let me leave the technical answer to that to someday when I talk about finding planets around other stars, but let me just tell you that potentially, yes, we can do that, but nobody is going to live there, because those stars that are that massive have lifetimes of less than a couple 100 million years. And that's just not enough time for life to develop, even if the planet's the right distance from the star. And after a couple 100 million years, the star is going to destroy itself and it'll destroy the planet too. So we might find some planets around those massive stars. One of the techniques is the technique I use, astroseismology. We're trying, maybe. Now, anonymous attendee, anonymous. What does the parachute design mean? Thank you for that question too. That parachute design for the little lander had secretly encoded in it a message. And I read that about a week ago. One of the people at JPL encoded in binary code, where you just use zeros and ones, a special message. And can I please ask you to look that up on the internet? Just look up the Perseverance lander and ask, what did the parachute design mean? Actually, Tebby, if you're sitting there with your phone, could you try to look that up? What did that parachute design mean? That was announced about a week ago, and I'm sorry, I simply have forgotten that. I'll come back to your other questions, Anonymous, in a minute. Let me see if somebody else has one.
Just,
sorry.
Sorry, go ahead. I just want to say, before we go to the other questions here, are there any questions from the floor? Shall we continue with these questions on video at the moment? Right. So the next question is from our Deputy Vice Chancellor for Research and Innovation, Prof. Frans Wanders, and he's an eminent scientist working on Frida Fort dome. So that question is really from an expert coming. So can you have a look at that one, please?
Right. Thank you for that question, Frans. Have you ever walked? Let me read the question, so in case the audience isn't looking. Don, have you ever walked the Frida Fort dome? I was one of the 3 guys that had it declared a World Heritage Site, and invite you when you can join me for a day's visit. Look at the rocks and enjoy the outdoors. 2 answers, Frans. The answer is no, I haven't. I'm sorry to tell you that, and yes, please, I would love to come do that. My hope is that when COVID allows and we can all be back on campus, I would like to give live talks at each of the campuses. And when I can come visit Potchefstroom campus live, yes, please, will you take me to the dome? I've seen it from the air flying over it many times, but I've not walked the dome, and I would love to see it. And congratulations to you to have it declared a World Heritage Site. It really is. It's the oldest crater like that that we know of on the Earth. And then one more question here from Haidar. My question is about the possibility of traveling to other galaxies and maybe habitable planets, for instance, using spacecrafts with antimatter fuels or even wormholes. Do you have any idea about the time of this revolutionary travel? Haidar, you are really talking science fiction here. Let's talk about more realistic possibility, and let's look at not other galaxies, just nearby stars. What is travel to the stars like? I'm going to tell you this story in more detail in a future talk, but we astronomers have discovered a planet at the right distance from its star to have liquid water, a rocky planet, probably with liquid water, orbiting the closest star to the sun, Proxima Centauri. Proxima Centauri is a tiny little red dwarf that orbits the famous Alpha Centauri, one of the 2 pointers to the Southern Cross. And it has a planet at the right distance to have liquid water. Might something be living there? Maybe. Now there's a rich American, originally Russian, by the name of Yuri Milner. He had the wisdom to be an early investor in 2 things called Google and Facebook, and that put several $billion in his pocket. And he uses that money to fund science, to fund scientific awards. And one of the projects he's funding is called Breakthrough Starshot. And the idea is to put into orbit about the Earth a cluster of little nano satellites, each of them about the size of a SIM card, and then with giant lasers on the ground, shine the light on them, and that will accelerate them up to almost the speed of light. Realize that at almost the speed of light, it will take more than 4 years for them to get to Proxima Centauri. You can't slow them down, so they'll go by at that speed, but they'll snap pictures and send them back to the Earth. That'll take 4 more years. If this project works, we might get pictures from a planet around the nearest star within the next couple of decades in the lifetime of many people listening to this. But for humans to go there, the energy needed to accelerate us up to near the speed of light so that we can use time dilation, special relativity, so that our lifetimes would last long enough to get us there is possibly beyond the engineering possibility. That's disappointing to somebody who loves science fiction, but it's possible. Nobody actually travels the galaxy live, but why send living humans? Why send living creatures? Why not send out artificial intelligence and robots? Even worse yet, or better yet, what if we create artificial intelligence that turns out to be smarter than us and can reproduce itself, and it can send itself out there? Let's hope if we do that, it still is fond enough of us that it allows us to continue. As for wormholes, that's a absolutely revolutionary idea that may not ever be possible. It's wild science fiction. And antimatter, well, if we can create antimatter in sufficient quantities, it's an energy source way beyond hydrogen fusion. But containing antimatter is an even bigger problem than containing the hydrogen in the fusion devices. So continue to read your science fiction. It's great fun to think about, but we're not anywhere close to bringing that science fiction to reality.
One question from the floor, Prof. Tebe.
Oh, the answer to the question.
Yeah,
right.
They're mighty things.
Right. Okay. Tebe has looked up the answer to what does the parachute design mean. It was encoded in binary code, and it means dare mighty things.
Apparently, it's based on a quotation from Teddy Roosevelt's missing quotation.
What is the quotation from, Tebe? Just a bit louder.
Teddy Roosevelt.
Oh, it's a quotation from the American President Theodore Roosevelt.
Yeah.
Dare mighty things. So, all right, thank you for that question. I'm sorry I forgot. I will now remember the parachute design. That was really perceptive of you to notice that that design was there. And it just wasn't the making of the parachute. Very good. Now, you had some other questions too. This object has, are we ready for asteroid 2009 JF1? This object has great probability to impact the Earth in May 2022. It was missing to include far, far out, the most distant object observed in our solar system. You're absolutely right. There is a new farthest object in the solar system. That's recent. I mean, that was in the news just recently. And you're right, I failed to put in far, far out, which is what it's called. Thank you for reminding us of that. What are we going to do about trying to stop these objects impacting the Earth and perhaps causing extinctions. I have a colleague named Pete Worden. Pete and I were students at the same time in the 1970s. I was a student in Texas, he in Arizona. He did his PhD at the University of Arizona, but at the same time, he was in the military reserve, and Pete grew up to be a 2-star general in the US Air Force. He ran Ronald Reagan's Star Wars program. He's a specialist in near-Earth asteroids. He was the director of NASA Ames Research Center in California, and he now runs, Yuri Milner headhunted him, he runs the Breakthrough Starshot project I was telling you about. And I once ran into Pete at the observatory in Hawaii, where I was observing. He was showing around the governor of Hawaii and some other people for a project. And I cornered him and I said, Pete, I'm worried about you because I think you're designing technology to deflect asteroids and make them miss the Earth if they're going to hit the Earth. And I know that in your time as an Air Force general, you also were in charge of weapons programs and you like to blow things up. And I'm scared that if you can deflect an asteroid and make it miss, you might go out and get one that was going to miss and deflect it and make it hit and have an even bigger weapon than you ever had before. I said, I'm more scared of you than I am of the asteroids. And he laughed at that. And he said, look, don't worry. We thought about it. If an asteroid's aimed at the Earth and you can find a way to push it, just give it a nudge, you can make it miss, push it in any direction. If it's not aimed at the Earth and you're trying to nudge it to make it hit, the Earth is just too small. We thought about it, we can't do it. Remember how tiny the Earth was in that picture as seen from Saturn? So pretty scary. They've been thinking about, can they do it? But they can't. And so the answer is, technologically, humans are trying to develop the ability to go out to asteroids that might hit the Earth and just give them a nudge, a variety of techniques, give them a little push so that they miss the Earth and save us the impact. Maybe we can do that. Maybe we can protect ourselves from it. And I'm sorry I forgot about far, far out. Thanks for reminding me.
Don, I'd like to ask you, I think many of our listeners are young scientists or prospective scientists and researchers. As experienced scientists, what advice do you have for people who like to start their career towards research and in science?
Okay. Thank you, Francois, for that question. I have a much more general answer than the question you asked.
Right.
What I advise you to do if you're young and you're starting off is follow your passion. What is it that you love to do? Go for it. Everything's interesting. There's nothing that's not interesting if you're passionate about it. So if that happens to be science, you'll have a wonderful life. Being a scientist is great, but boy, are there a lot of other things to do in life too. And if that's where you're headed, go for what you love most. You need to do something that you'll make enough money to get by. Some of you probably want to be rich. All right, if money's your thing, then people who do that are interested in making lots of money too. But if you're a scientist, if you're an academic, you have enough. And once you have enough, other things in life are important. If you've got nothing, money is everything. And I understand that that's true of a very large fraction of the people here in South Africa. Then it's everything. But if you're going to have a life with training, do what you love. The money will come, you'll be comfortable, and then you'll be happy too. Follow your passion.
Yeah. One last thing, and I'm going to put you on the spot here, Don. In the late 70s, Voyager sent out information about human life and culture outside the world, of the orbits to other civilizations, and a lot of eminent people and scientists were asked what would they put on that on those plates as a message to other possible life forms. So, what would you send if you have a chance to send information out?
Well, I didn't get to make that decision, Francois, but one of the people who governed that, who was decisive, was a man named Carl Sagan, who was an eminent astronomer and public outreach person. I'm going to tell you in a minute what they decided, and I think they made good decisions. But let me tell you, just as an aside, Carl Sagan also did incredible public outreach. He ran a program called Cosmos. He wrote books. He died, unfortunately, very young from my point of view. He was only 62 when he died. His wife has carried on the tradition. She also is a scientist and a movie maker. Her name's Andrew Yan. And she funded, 20 years ago, a great movie called Cosmic Africa, about a young man growing up in Mahakeng, who grew up to be a famous astronomer. His name's Tebi Madupi. He introduced me here. And they made a movie about traditional African astronomy. And on one of my future visits, we're going to play that movie too. And Tebi will play that movie and take your questions. It played internationally. She funded that. out of the kind of money that came from what they did. Well, now, they decided for that plaque that went out on Voyager to put on examples of many different human languages to try to show the breadth of human culture. They put in simple mathematical relationships in binary code, thinking that an alien intelligence would understand binary and would be able to try to decode that. They put in a map of the solar system pointing to the Earth, and some people feared that, what if the aliens find that and then they know we're here? I'm not really worried about that. I told you a little while ago, it's a long way out to the stars. I'm not worried about them coming to get us. And by the way, they're not here yet. We'll talk about aliens on some future talk. They're not here, they haven't been visiting, and I'll tell you that story in the future. So they put human culture, they put messages of peace, they put scientific messages in, they put some simple binary mathematical code to try to help any alien intelligence to try to decode this message. But they put it on a thing that has now left the solar system. At the speed it's going, it's not aimed at any star, but if it were aimed at Proxima Centauri, the nearest star, it would take about 26,000 years to get there. And that's the nearest star. It's a long, long way to the stars, and space is really empty. I don't think anything's ever going to find Voyager. But it was fun to send it out there.
Anything you would put on it if you have a chance now?
Me, no. I like the choices they made. I think they made good choices.
I think that the last question you have from the floor. Yeah. Last.
Thank you. Okay, let me answer that. The question was, many of the planets and other things have got these traditional names. So I'm actually going to answer it, and I think you're not going to like my answer. The planets move through the stars, and humans look up, we can see the planets are moving through the stars. 3,500 years ago, in what we now call Babylonia, modern day Iraq, people looking at the sky said, why do the planets move through the stars? And they came up with a theory. They said, the planets are gods, and the gods do as they please. And that's, out of that, astrology arose. So astrology is the belief that the planets are gods and the gods can affect human lives. The planets are not gods. I was just showing you pictures. We know what they are. They're not gods, and their positions have no effect on human life. But culturally, it's interesting how that arises. And it's a cultural happenstance, and it's a story I will tell in another talk, how it is that astronomers chose to take a history of astronomy arising in the Middle East, coming through Arab culture, through Greek culture, to Roman culture, to Europe, and then that spread around the world as what astronomers use as our standard names. All these constellations, all these stars, all these planets have got names in everybody's culture. Here in South Africa, the star cluster we call the Pleiades, from the Greek, the Seven Sisters. In Zululand, it's Isilimela, and it's important for the manhood ceremonies. The constellation we call Orion, with its belt, down in where I live, down in the Eastern Cape, that is not the belt of a giant hunter, it's three zebra. And I actually like the idea of these three zebra across the sky. And so there's no reality in that, but it's very important for human culture. And that traditional astronomy it's great fun, and it tells us about us humans, but it's not an answer to what is happening in the universe. Okay, that's probably a good place to stop.
Yeah, that's right.
Tebby, can I turn this back to you?
Okay, thank you. All right. Once again, thank you very much. Thank you, all of you, for supporting us and for attending the webinar. Now I'll hand over to Professor Drummond, the Deputy Dean in our faculty, to give vote of thanks. You have 2 questions. Oh, there's still more questions? Oh, you want?
No, can we move them?
Okay. Is that okay?
Yeah, thank you very much, Tebo, for giving me the chance to give the vote of thanks. John, you really took us on an amazing trip. You took us on a trip around the world, what we call the world, which of course is our Earth. You took us to our closest neighbors, to the moon, Venus, Mars, all the planets. I so enjoyed getting that perspective. It was really wonderful. And the way that you were able to provide parallels between things that happen here that we're familiar with, our weather events and so on, and how these happen on such a much grander scale elsewhere in the solar system, let alone, of course, the rest of the universe, that we're looking forward to another talk on all of that. I know I grew up knowing that many vegetables eaten make John strong, unbeatable, nearly, and now we have to cut off before perfect. But I think you also explained very well why Pluto had to be cut off at the end, but it does mean that my sentence is now not complete. So thank you so much for your talk. I think I'd also like to thank Tebe in particular for setting all this up and for bringing you here. We really appreciate that. Thank you to David for his introduction and for Francois for handling the questions. And I know Marilyn, our DVC, would have liked to have been here in person, and it wasn't possible.